All right, we just went live, so I will introduce today's speaker and then we can get started. So today I'm happy to have Dr. Larry Kepko here with us. Larry got his Bachelor's of Science in Astrophysics from UCLA. He continued at UCLA, receiving his MSc and PhD in Geophysics and Space Physics in 1996 and 2001. He then moved to Boston College, where he began work as a research associate before becoming an adjunct professor and senior research associate. In 2007, he moved to the University of New Hampshire Space Science Center and is now a research astrophysicist at NASA's Goddard Space Flight Center. Larry's research interests are focused on tail dynamics and understanding substorms and their onset mechanisms, periodic density structures in the solar wind, and their effect on the magnetosphere and on their magnetosphere as well as small satellites. Larry has also worked extensively serving our community, co-chairing the 2012-2013 Heliophysics roadmaps. He served as an editor for JGR Space Physics and as an IAGA division lead. More recently, he's been advocating for cohesive collaborations between international space agencies in order to address more impact science with larger and broader scope. And today I'm happy to have Larry here to talk to us about this more recent work and his latest project, ISTPNext and Heliophysics Great Observatories. With that, Larry, if you'd like to take it away.
Yeah, thanks, Kyle, for the nice introduction. As Kyle said, I'm going to be talking about something called ISTPNext and Heliophysics Great Observatories. I guess I should add a disclaimer that what you're about to hear is the opinion of community members, is not necessarily an endorsement by NASA per se, even though I have NASA by my name. I do not speak for headquarters, but headquarters is very well aware of what we are advocating here. So this work is in collaboration with a long list of people. The COSPAR task group on establishing an international geospace systems program I'll talk about in halfway through the talk. All my co-authors have been working over the last year and a half or so on these topics. So the background for this work started about 2 years, maybe a year and a half ago. At the time, we had a very magnetospheric focus. And the reason was because I'm primarily a magnetospheric physicist. And I looked around the landscape. We had Helio 2050 in the US. We have the US Decadal Survey just starting up. And the question is, where is the magnetospheric community going? Themis today is 16 years old, hard to believe. Geotail was just turned off after 25 years. Cluster is now ending its lifetime, hopefully not this year, but no later than maybe 2 years from now due to deorbiting. Those are key components of what we call the ISTP program and really the magnetospheric research as a whole. So where are we as a magnetospheric community are going? Where do we need to go from the science perspective? At the moment, there are very large gaps in our magnetospheric knowledge and in our magnetospheric program. So in that gap, this group was formed to try to help fill in some of those gaps and define what a program might look like. Well, at the same time, the ITM community is planning for a very large effort at the end of the decade with the launch of GDC and Dynamic at the end of 2029. It's a fairly extensive effort to understand the system that I will talk about in a few slides. It's not just GDC and Dynamic. Concurrently, Solar and the heliospheric community currently has a very active program. So we have big missions like Parker, Solar Orbiter, and DKIS, Ground Observatory. And coming online fairly soon, next few years, Punch, Muse, and Solar C, competed US missions. There's also an Indian mission launching fairly soon as well. So very active program there. ITM is planning a very large active program at the end of the decade, and Magnetosphere would like to have a very active program at some point. So each heliophysics discipline is facing seemingly different challenges and opportunities, but there are really some common threads. Looking forward, as a community, how do we, A, link these threads together and develop a unified worldwide heliophysics community? We've become a bit disjointed since ISTP era in the early 2000s. COVID did not help. We're not as cohesive as we used to be, and that's causing difficulties, I would say, making our science not as strong as it possibly could be. And then also, how do we best utilize the assets that we have, ground, space, and modeling, and ensure a future science architecture that is responsive to our needs? So independent of whatever missions we fly, we often get focused on the big space missions. What does the architecture look like that sort of incorporates those missions, incorporates the ground-based community, and incorporates the modeling? Again, we sort of lost focus here on what architectures look like from the science perspective. So in order to know where you're going, you really need to know where you've been. So lots of different quotes on this. Maya Angelou has one. You don't know where you're going until you know where you've been, which is a true statement. If you have kids like I do, or just happen to be a big Disney fan, you might know Moana. Wayfinding, it's seeing where you're going in your mind by knowing where you are, by knowing where you've been. And that's Maui, of course, demigod of the wind and sea. So in order to figure out where you're going, you really have to have a clear idea of where you've been and where you are at the moment. And that brief intro brings us to today's talk, where I'm going to argue that we need a new program and call it ISTPNext, just for now, because people, I think of a certain era, at least know what ISTP was. And then introduce the concept of heliophysics great observatories. So I'm going to step through really three things. One is, where have we been? I'm going to talk about the 4 eras of heliophysics, which are just useful ways to organize our discipline over the last 60 years or so. And then talk about where we are. And where we are is that all disciplines within heliophysics are trying to study their systems as systems of systems. And I'll talk a little bit about what that means, with a focus on the mesoscales, that middle scale between micro and macro. And I'll talk about where we could be going, again, not officially, possibly where we might be going, which is the concept of great observatories and ISTPNext. So where have we been? Well, heliophysics has had 4 primary eras. Of course, there's a prehistory prior to 1958, going back hundreds of years or more. But here we're talking about the space era, the launch of the first satellites. We had the first era of discovery era regions, 1958 to about 1975. Then we go through that dynamics from 75 to 90, ISTP from 90 to 2005, then the era of microscales. I'm just going to step through each of these really quickly. So the era of discovery regions started with the launch of the very first satellite, Explorer 1 and Sputnik 2 and 3, which discovered the radiation belts. Just by their very nature, every launch was a discovery because we had not been there before. So you put the instruments, you thought you might see something, launch them, and you see what's up there. It's important to remember that even at this time, the very first era happened in the IGY, the International Geophysical Year of 1957 and 1958. Exploration of the solar wind and magnetosphere has always been an international effort. It always will be an international effort. International organizations such as COSPAR and COSPAR, which exist today, grew out of those cooperative mechanisms that were established during the IGY. In fact, things like the World Data Centers were established. If you're familiar with the Kyoto indices, that's World Data Center C2 that was developed during the IGY. Right, so we know that Explorer 10 discovered the magnetopause just by flying. Explorer 18 discovered the battle shock. OSO 7 and Skylab discovered something called coronal transients, which turned out to be CMEs, and so on. And then at by the early 70s, we had a pretty good idea of the basic contours of the Sun-Earth interactions and solar dynamics. And then we set out to discover the dynamics of those regions. So this is the second era of discovery. And for the most part, these were multi-spacecraft missions and all international. So HEOS 1 and 2, for example, high inclination, high altitude, led by Germany. Helios A and B, which prior to Parker was the spacecraft that went the furthest in, looking at solar wind. IC1, 2, and 3, if you're a magnetospheric person, you know all about IC1 and 2. You can't really understate the importance of those 2 missions for understanding tail dynamics, the launch in the late 70s. Then you had AMTI, anti-IRM, CCE, and UKS, which is a trilateral between the UK, Germany, and US. And of course, had the barium release, lithium, I guess it was lithium in this case. Oh, both, yeah, it was both, lithium upstream and barium downstream. To trace those particles as they traveled through Earth's magnetosphere. Atmospheric explorers, Prognos, and Intercosmos. So, all international multi-satellite, for the most part, missions trying to disentangle the temporal and spatial dynamics. And then by about 1990, the community understood we needed to study the system in a coordinated fashion. Right? Even then, we knew the pieces were linked together, and we had to focus on them at the same time. So in 1980, NASA completed the OPEN program, the Origin of Plasmas in Earth's Neighborhood. Instruments were selected, money was going out, but then it was de-scoped and pulled back from 4 spacecraft to 2. Those ended up being wind and polar, and then turned into something called the GGS program, or Global Geospace Science Program, which was just at that time wind and polar for spacecraft. International contributions turned this into what we call the ISTP program. The core spacecraft consisted of wind and polar from NASA, ISS, which was the progenitor to JAXA, contributed GeoTail. Equator was descoped from the US side. Germany launched Equator S, which unfortunately failed within a few months. SOHO was a really critical mission for solar observations. Joint ESA-NASA mission still exists today, of course, as you all know. And then we had other missions that came online. Cluster Akabono, Stampex Interval, all the LANL and GOES data, back when the LANL data were available to everybody, all participated, right? We're all one big community trying to understand the interaction of the sun and the earth. Things like data standards were established. You go to CDAL Web, which exists today, where you get all your data from, Coordinated Data Analysis Workshop, which don't exist anymore. And if you look at the standards, it's ISTP standards, right? The CDF standard, all came from this era. It's important to remember that the core program was endorsed by something called the Interagency Consultative Group, or IECG. It doesn't exist today. But because it was, that was an interagency group between Japan, Europe, Russia, and the United States with NASA. And it had real decision-making power. And when it said we should do something, things could happen because it was interagency agreements. And it unified our worldwide community under the common scientific objective of ISTP, understanding the flow of mass, momentum, and energy through geospace as it comes from the sun. And so when you have a common architecture, common program like that, it makes it very easy to plug things in from the outside. But ISTP was much more than spacecraft, as you're probably all aware. It had an explicit theory and modeling component. Those are the first 4 recipients of awards from the ISTP program, theory program. It had a ground-based component. And these are my 2 fun facts for ISTP. The first funding for the Super Darn radar came out from NASA, from the ISTP program. Right, NASA does sometimes fund ground programs if no other ground program exists, which it didn't at the time. Fun fact number 2 is Canopus grew out of the Open GGS ISTP program as well. And those of us in a certain area grew up on Canopus data. There's a paper from Rostocker and Sampson from 93. The O in Canopus stands for open, right, going back to the 1990 program. And really, again, for those of us who came up during ISTP, it's really a shining example of how coordinated worldwide efforts can be brought to bear on a really intractable problem. And then once we knew the big scale interaction, the coarse level, system level understanding, we realized we had some pretty major gaps in our understanding of the microscales, or what we call kinetic physics in simplistic terms. One could imagine that just by understanding the macro scale, the boundary conditions, and knowing the basic physics, you could just simulate your way to knowledge. We know that's not quite true anymore, which we'll get to in a little bit. So the aerial microscales are meant to focus on some of this kinetic plasma physics. Van Allen probes in Arase looked at the physics of acceleration and transport of radiation belt particles, things like wave-particle interactions. And then this, of course, is looking at electron scale magnetic reconnection. Parker Solar Probe is really kinetic plasma physics laboratory, as is Solar Orbiter. In fact, the ESA website calls it a complex scientific laboratory. Spent a lot of time in the last 20 years or so really looking at the microscales. So where are we today? Well, ISTP established the large scale coarsely, right? We learned a lot about how our system works as a system through ISTP, statistical studies, averages, the initial numerical simulations. And we studied the small scales extensively with MMS and Van Allen probes. But in between is what we call the mesoscale, just by definition. And I'm going to argue in the next few slides that really the 5th era, which is being defined now, should focus on mesoscales, the linkage between the small scale and the global, and from the global to the micro, and study each system as a system of systems. I'll talk about what that means in a minute. So by system of systems, we simply mean any system that can operate independently, like the human body, for example, all the different systems of the human body. But when you integrate them together, you yield more complex and sometimes unexpected behavior, right? Something called emergent dynamics, for example, things you would not have predicted by putting things together. So the link between gum disease and heart disease is one of those things that if you were studying just gums or studying just the heart, you would not have thought, oh, why are they linked? If I have gum disease, why does that produce heart disease? That's not a thing that you would necessarily find by studying them independently. It's only when you put the system together that you see the linkages. And everything we study in heliophysics, the sun, geospace, because it's a magnetosphere and ITM, is a system of systems in the same way that a human body is, right? The sun has all these different layers of the inner region below the photosphere, and the photosphere, the chromosphere, going out to the different layers of the corona. It's not just one monolithic corona, it's different layers, and then it goes out to the solar wind. They're all linked together through different scales and different interactions. Magnetosphere, of course, consists of the inner magnetosphere, plasmasphere, ring current, things like that, which itself is a system of systems. The tail, the magnetopause, the magnetosheath, the bow shock, linked again to another system of systems, the ITM system, ionosphere, thermosphere, mesosphere, where the neutrals and the ions collide in a very complex fashion. If you were to study, for example, in the ITM system, just the neutral gas all by itself and learned all about the physics of neutral gas dynamics, and then study separately the physics of plasma dynamics, you couldn't just put them together and say, now I understand ion-neutral coupling. It's not how it works. You have to study it as a system of systems. Systems, for the most part, are driven by physics at 3 scales just by definition. Micro, sometimes called kinetic, meso in the middle, and then macro, which is a significant fraction of the system scale size. This picture is for the solar wind, but you can make a similar chart for your favorite system if you want. Here on the left, for example, in the solar wind, we have wave-particle interactions, little reconnection areas too as well. Those are kinetic scale features, size of the ion, electron motion. If you're a turbulence person, that's down here in the dissipation scale. Switchbacks kind of straddle the line between kinetic and meso, at least at Parker. Earth's magnetosphere, interestingly enough, from the standpoint of the solar wind, is a mesoscale size feature. It sits in the solar wind flow within the mesoscale regime. Things like periodic density structures, these are things in the solar wind I've been studying for quite a long time. They sit firmly in the inertial scale, right? Where you get in the cascade, and then things like streamer blobs, if you're familiar with Scheele blobs, things like that coming off the helmet streamer from the sun. Microstreams are basically switchbacks, but observed a long time ago with Ulysses. And then you get the things that are much larger scale, that are imposed by the sun itself, stream interaction regions, CMEs, and so on in the energy container scale. So these 3 different, if you think in terms of turbulence, 3 different turbulence regimes, dissipation, inertial, and energy containing. But if you think about it in terms of dominance, it kind of becomes interesting. So anything at the, say, electron ion scale clearly was evolved en route from the sun to L1, right? Nothing injected at those scales survives to L1. It's all evolving en route through turbulent cascades or interactions, things like that. If you go at the opposite scale, at the very large scale, well, CMEs are clearly injected into the solar wind. The structure of SIRs is injected or imposed by the solar surface. And that's clearly injected and imposed. And in the middle here, it mixes. Some things are evolving, some things are directly imposed by the sun. And that's right in the middle of the mesoscales. And the mesoscales are a messy regime because they are really balancing stuff from the kinetic and stuff from the large scale. Mesoscales are really critical because they connect micro to macro and they connect macro to micro. Just by definition, if macro says do something, it has to flow through the mesoscales to get to the microphysics that actually produces the response. And mesoscales connect the system of systems, as we'll talk about in a minute. And mesoscales are really inherently difficult to observe and simulate. Any in situ spacecraft is inherently a microscope, is observing the microscales with in situ measurements. To get to the large scales, you go to remote sensing, right? Take a picture and get the big scale. But as you go towards the middle, you either need lots and lots of in situ measurements or really fine spatial and temporal resolution imagers. And both of those leads to mostly funding problems, really not really a technology problem. And then simulation tools is the same problem. If you start from the bottom and work your way up, you get to fully kinetic and you run into a roadblock, computational power. MHD, you start at the large scale, move your way down, and you run into a roadblock, computational power. There are techniques to try to straddle this regime, hybrid codes, things like Glaciator, for example, is trying to straddle this a little bit. But inherently, again, that middle scale is difficult, right? You're bridging 2 scales. And the boundaries between kinetic and microscale, between mesoscale and global, are fuzzy, because these transition regions usually are fuzzy. And that makes them very interesting from a science perspective, but also very difficult to study. So Earth's magnetosphere, as I think you're all probably aware, is a system of systems, right? This is a simulation picture from the, and this is probably Gamera. This represents what the magnetosphere may look like and may not look like. Probably pretty close. I don't think we understand all the little details if those are real or not. But mesoscales are basic elemental units of mass and momentum transport, at least in Earth's magnetosphere, probably in the solar corona as well. They couple micro to global. For example, reconnection, which is a microphysical process, produces mesoscale flows. Mesoscale flows produce a global response. And vice versa. Global solar wind forcing leads to thin current sheets, leads to reconnection, and then BBFs coming out. So that coupling is two-way between micro and macro. This simulation snapshot shows the 3 key regions for magnetospheric mesoscale dynamics. The day side, FTEs, hot flow anomalies, Kelvin Helmholtz, all firmly in the mesoscale regime. the nice side plasma sheet, bursty bulk flows, and the inner magnetosphere with particle injections, plasmaspheric boundary dynamics as well. If you study the systems in isolation, like we often do, you study the tail, or you study the inner magnetosphere, or you study the magnetopause, and you try to stitch them together, you'll miss key dynamical features. And that's what I mean by a system of systems, right? The whole is greater than the simple addition of the parts. And we all understand this, right? If you studied Van Allen probes, you understood what was happening locally, but there are a lot of times you really wish you knew what that outer boundary condition looked like, so you knew what was coming in. But it's not just Earth's magnetosphere. Again, in the solar corona, within a few our sun, the solar wind becomes highly structured with radial flow. So out here, maybe, I don't know, 4 solar radii or so, 3 or 4 solar radii, you get the structured solar wind that we know and live in right now, right? But if you look down, and it's again different instruments, which is part of the problem, you see a lot of structures, right? A lot of time dynamic structures, a lot of spatial structures, firmly in the mesoscale range that somehow couple the things that emerge from the solar surface to this sort of structured radial flow. And this is one of my favorite movies to show on the bottom right. This is taking a picture of one of these little square here, right, showing solar radii. So this is 5 solar radii by 5 solar radii square. So a little square taken from up here somewhere. And it drops in Earth's magnetosphere to scale, right? So this is us living in the solar wind. And all these little blobs and structure here coming from the solar wind, what we call solar wind mesoscale structures, the kind of things that I like to study recently. And all these structures that are all the time, they're buffeting Earth's magnetosphere. That's sort of the daily space weather that Earth's magnetosphere get. And you see from the standpoint of our world, we're pretty small, but from the standpoint of the solar wind, we are a mesoscale structure. So it's really important to get not just the CMEs, which is the big stuff, but the mesoscale structures that drives our dynamics every single day. It's also the day side, I mentioned earlier, the foreshock, magnetosheath, transients, flow anomalies, things like that, Bow-Stuck structures. Those are mesoscales. And these are the kind of things that you wouldn't get just by saying, the solar wind turns south, magnetosphere responds, right? You don't get hot flow anomalies. That's a kinetic effect that's due to the interaction of the solar wind with the bow shock. And it's really these kinetic simulations that pull it out. Right? They have a significant impact on the magnetosphere that's not really quantified in any meaningful way at the moment. In the magnetotail, of course, we know that global models and ground-based observatories suggest mesoscales are ubiquitous in the tail, right? But if you look at the figure from the bottom right, this is from Vasilis's paper from the mid-90s, showing a conjunction of anti-IRM, IC2, some GOES satellites, kind of shows this idea of a spreading flow burst. We haven't really done much better than this, I will say. Even if you had THEMIS, which is the equivalent of what's way over here of IC, 1 spacecraft, and then maybe MMS down here, equivalent of 1 spacecraft. Here we are 25 years later, not really done better than this picture. And it's simply inadequate to really understand this, the kind of thing we see in simulations, which is a magnetotail full of mesoscale structures, which we think are there. The ionosphere seems to tell us they're there. We don't have any quantifiable information about what is happening out there. Of course, in the inner magnetosphere, all the stuff out here in the tail, these mesoscale features from the tail come in and feed the inner magnetosphere with mesoscale structures. Right? So it's highly time-dependent, highly structured, which should lead to highly structured, highly time-dependent inner magnetospheric response. We know the plasmasphere also is structured in response to driving, shoulders, drainage plumes, and things like that, which again impact things like wave growth and particle acceleration and diffusion. So understanding these linkages are really important for understanding the full system end-to-end. Of course, in the ionosphere, we know from the THEMIS era that we get these optical signatures of mesoscales all the time. And this is a picture from Nishimura from a while ago. What we see observationally are the white light streamers. And then notice what it says, inferred flow, right? We think there's flow here. We don't see it because it's invisibility on it. The flow itself is invisible. What we see is just the upward field line current part of the presumed flow burst coming in. There's this huge gap between ground-based kind of stuff we get here in the ground-based and in situ observations that can only be resolved by resolving mesoscales in Earth's magnetosphere. So the system of systems approach and mesoscale dynamics are really universal, includes magnetospheric, ITM, and the solar heliospheric community. What's nice about a common framework, though, if we can get one, is that we start speaking the same language as a community. Right, we start saying system of systems, we start talking about mesoscales. It doesn't matter if I work in the sun or the solar wind or the magnetosphere or the ITM. We can all start to understand each other. Policymakers can start to understand us and think of us as a unified community. So you can imagine a common scientific framework like ISTP had, but instead of Sun Earth connections like it was before, it's mesoscale or connector or messenger physics. And it really would link our community together under a common scientific objective. But in order for something like that to happen, there's really two key missing elements. First is we don't have the necessary observations. So we look at something like the sun. We have, of course, the HSO, Heliophysics System Observatory. System's right there in the word, in the acronym. It does attempt this coordination in pursuit of system science, but doesn't do a good job because coordination is ad hoc, it's accidental, and totally inadequate for the mesoscales. And the reason for the inadequacy is that each mission that is part of the HSO is responsible for its own science objectives, which are totally independent from every other science objective of every other mission. So this coordination just happens after the fact. So here's an example here on the left showing from just last week. In yellow is SOHO and blue is stereo. Stereo has actually come around, like it's getting pretty close to Earth, it looks like. And you see right now we're only getting half of the sun, the front half. The back half we don't get a picture of. It's actually even worse than that because we don't get the poles. The poles, from an imaging standpoint, are totally unexplored, and I would say is pretty low-hanging fruit in terms of a mission. If you want to take a picture of someone we haven't taken a picture before, go over the pole and look down or look up. So sparse measurements, even if they're coordinated, as they are here in stereo and SDO, simply don't capture the full system, right? It's missing key portions. If you go to Earth's magnetosphere, again, sparse measurements, even if coordinated, do not capture the mesoscales, right? So there's two aspects here. So here, for example, is MMS, Themis, maybe the Rossi's over here, some GOES. If you look at this picture, you're like, what are we trying to do? There's just simply no way we'll capture the dynamics in any meaningful fashion with these sparse measurements. We look at local things, right? We look at small scale things. The second obstacle is the lack of coordinating body with real decision-making capabilities. We don't have that anymore. We had it with ICG and we don't have that anymore. We'll talk about that in a minute. So where we're going, to some sense, back to the future. We don't need roads, of course. We need a large undertaking to answer many of our key science questions that remain open. And the KL survey right now is going to tell us what those are. We already know to some extent what they are because we fed those white papers in. And there's a lot of common themes. It's systems of systems. It's the middle scales. It's how the systems coordinate or talk to each other, how they work together, how they modulate each other. And it's really science that centers around the ITM, the sun heliosphere, really sun inner heliosphere, and magnetosphere as systems of systems, with mesoscales playing a key role. So we need a large undertaking if we're going to answer those kinds of big questions. The current fleet is totally insufficient for these kinds of questions. We'll always do great stuff with explorers and equivalent and ESA and JAXA, but to do the really next level stuff, you're going to need something big. And the geospace and sun inner heliosphere are simply too large for any single agency to go alone. We've known this throughout the history of the space age. We've always been a coordinating science. So we need an intentional forward-thinking coordination mechanism and a new worldwide effort that has to resolve the mesoscales simultaneously across a system of systems. And for geospace, that probably means a mesoscale or a fluid backbone to stitch the system together. It's a lot of spacecraft combined with remote imaging, particularly in the inner magnetosphere, maybe the transition region where you can do it. Daytime magnetopause, for example, soft X-rays. Imagine if we had just kind of those three measurements: inner magnetospheric imager, like a MagCon type thing, and imager of the magnetopause and auroral imaging, all working together, right? That'd be pretty fantastic, but no single agency can ever do that by themselves. Not going to happen. And then you have in the solar heliosphere, mesoscale grids and tight coordination with imaging. Right now, they're kind of, they have lots and lots of imaging, but really not a lot of in situ truth. You also need to monitor the state variables. For the magnetosphere, I call these Earth's vital signs. L1 measurements, EUV imagery for the sun, auroral imagery for Earth, cross-bill cap potential, radiation belt content, things like that, that you can feed into your models or provide sort of the background context of the observations that you're making. We also need to start making advancements in next generation numerical modeling. This models that will have in 30 years will not look like the models we have today, but in order to get there, you need to start them today. It takes a long time to develop new models, and they need significant investments. GI program funding of $100K a year are not sufficient to generate new numerical models. We also need to organize the ground and space-based communities around programs. All too often these days, we organize around a mission. Right, so Themis also had an imaging array, which is fantastic. It's a tiny piece, though, of the available resources that we have available. So we want to organize around programs. That's what I'll talk about with the Great Observatory idea. We also need to embrace and utilize big data, AI techniques, and universal standards. I don't want us rushing off to this field without really understanding the physics for all the obvious reasons, but we should learn to use them to our advantage in the same way that earth science does. All these activities and initiatives are globally coordinated and working together to study geo and solar inner heliosphere holistically as systems at the scale sizes we know are driving the dynamics. And it's really those two key pieces that are missing, the holistic system aspect and the mesoscale observation numerical gap. And really a next generation ISTP type program is what I'm arguing for here. So our first chance to make this happen is with the ITM community and the upcoming GDC plus dynamic mission. This is a standard chart of what you might get with a mission if we operated as normal. So first we have GDC, which is already well underway. Our instrument selections, our interdisciplinary science teams are all selected, and we're off and running defining that mission. Dynamic will be a PI-led mission. I don't know when the AO is coming out pretty soon, I guess. The plan is to treat these together, integrate them together, because we will launch together, we'll make measurements together and treat them as a, I don't say a single, they're not a single mission, they're separate missions, but with shared objectives, let's say. GDC will use some ground data, of course, for CalVal. I'm going to talk about why that is really, we should think much bigger than that. And then we'll use models, just like every mission does, right? Data assimilation, whole atmosphere, couple models, high resolution, multi-scale models. And in our little, group here within GDC, we'll do GDC and dynamic science. That's the traditional mission architecture for a NASA type mission. But there's a lot more out there, right? In terms of space-based missions, there's all the stuff that NASA does, right? Awe, AIM, Time, Gold, EASY, and so on. There's other missions out there. Korea is doing rockets and SNIPE. ESA has Swarm. There are other agencies, particularly India and Korea, are very active in this field, and we need to pull them in. How do we pull those data from all those spacecraft into a common program, right? We also have ground-based measurements. There's a lot of ground-based measurements out there. Ground-based observatories are doing great science on their own. In fact, rather than say, well, how can GDC use ground-based? You might say, well, how can ground-based use GDC? I just flip it around. There's a lot of things you can do if you pulled in and integrated them on equal footing in a coordinated fashion. But at the moment, we're all kind of siloed, right? Your spacecraft works independently. If you work on SuperDARN, you do SuperDARN work. If you work on ISRs, you do ISRs work. We really need to pull everything together under a common framework, again, the way that earth science really does. And simulations and theory, there's a lot outside of our program that is not funded through the IDS or through GDC in particular, community developed models, and the NASA Drive Centers, right? So I think Slava talked about the CGS Drive Center last month or a couple of weeks ago. That is not formally part of GDC, and yet they're doing fantastic modeling that I would like to see in GDC somehow. We need to figure out a way to incorporate them. And currently there's no process to do that, which is really quite unfortunate. It's just wasted resources. And then we have things like standing rockets, balloons, and CubeSats, and presumably people will do underflights of the mission, and incorporate CubeSat constellations into our overall mission architecture. So there's a lot more we can do. And in fact, and if you pull all these things together, you could think of pulling them together under the concept of an ITM grid observatory. So if we're back here, right, I might just do all of this and say, we will answer GDC and dynamic level one requirements, our science questions, declare victory and go home. I find that very unsatisfactory. There's all this stuff out there. We combine them together. I can answer the GDC and dynamic questions, plus all the other questions that everybody else wants answered in a holistic fashion. So the plan is to use GDC and dynamic as a focal point for international ITM research, utilizing ground-based, space-based, and numerical simulations, all together, integrated together, and produce not just GDC and dynamic science, but comprehensive coordinated ITM science, right? Stuff that you wouldn't be able to do if you didn't integrate everything together. And then, of course, we'll feed into operational space weather forecasting as well. Now, we're doing this. The GDC team, I'm part of the GDC team as deputy project scientist. We're doing this. I show this chart all the time. Bea Garlo-Cord, our ground coordinator, is a group of 200 plus people that are part of the GDC ground. Jared Bell is our model coordinator, trying to work and integrate the models. I'm the international lead, trying to pull in international partners. We're going to make something like this happen for GDC and dynamic. It's all within the GDC program at the moment. I'm hoping something else maybe comes in to help augment that. Because the problem right now is an organizational mechanism does not currently exist. There's no ISTP program, there's no IACG. So we're trying to fold it into the GDC program and do the right thing here. The concept of great observatories, which again, we're going to try to make happen by utilizing GDC as a strategic hub, forms the basis for what an ISTP science architecture might look like, ISTPNext science architecture. We bring in all of our assets, space, ground-based measurements, simulations of theory, and sounding rockets, balloons, and CubeSats, and you pull them all together into comprehensive coordinated science. No more, still be able to do your individual science, but really no more of the siloed, localized studies. We have big questions we need to answer. We have a big community. It's time to pull them together again, like we were 20 years ago, 20 plus years ago. And you can have a comprehensive coordinated ITM science, magnetospheric science, and solar and heliospheric science. And this formed the basis of an ISTPNext program. Now, on the MAG side, we're a little weak because we did not have anything in the last decadal survey, and we'll see if the next one changes that. Solar and heliosphere is interesting. They've been thinking exactly the same thing. So the PUNCH mission, which launches, I think, next year, they've been thinking about the exact same thing. There's all these assets out there. How do we pull them together into what is effectively a solar and heliospheric grid observatory? So these things are happening. The thing I want to point out is that the science architecture is independent of mission implementations. We also often get wrapped up in what is the next big space mission. We don't need to think that way. Whatever the next big thing is for magnetosphere, it should look like this, right? So we do have an opportunity to define the new era, the fifth era, we're calling it, focused on mesoscales and cross-system coupling. As you know, GDC and Dynamic are the last of the strategic heliophysics missions from the decadal survey. There's nothing in the queue after that. It's just totally undefined. So the decadal survey has a pretty difficult job ahead of them to define that future. I think the release will begin early to mid 2024, give or take, and that'll cover the next 10 years of NASA and NSF and NOAA science. Concurrently, ESA is competing this next medium class missions for launch in the 2030s. There's also the opportunity for what we call missions of opportunity, particularly on the Earth science side. Plasma Observatory is one mission I know that ESA is looking at, and that would be like a sort of a microscale mission. It'd be great if we could coordinate something, maybe does mesoscales at the same time. And then JAXA is also discussing their next competitive medium class missions, launch in 2030s. One reason I did this, because about a year and a half ago, I heard that JAXA was working on something called FACTORS. And FACTORS was, again, a medium class competed mission proposal to do sort of auroral current system type stuff. But when I talked to the community, the European and US community, hardly anybody had ever heard of it. It was if it had been selected, it would have been a pretty important mission for us to know about, to integrate with GDC. But we didn't even know about it because those lines of communication just aren't really there at the moment. So we're going to try to fix that. So FACTORS didn't go forward, but they are working on what their next mission might look like. Again, with launch in the 2030s. So you can think right now it's 2023. 2030 seems like a long way off, but these missions are being defined today. There's additional agencies out there, particularly India and Korea, which are very active. How do we coordinate all these different things so that we can actually do the science we want to do? So I think the 2030s could be another golden era for internationally coordinated heliophysics science, answering some very fundamental questions about how we interact with the sun and solar wind. But it's not going to happen by itself, and you can't expect the agencies to do it by themselves because they won't. It has to come from the community. So what can we, as a community, we don't have to wait for the agencies. We don't have to wait for the decadal. We're not defining what missions to fly or what science to go after. We're talking about science architectures. No matter what you do, you should have a science architecture. So 3 things are happening over the next year where we can have these discussions. The first is a symposium on the future of heliospheric science from geotail and beyond, so celebrating the life of geotail, but what's next? Beyond geotail, March 28th to 31st, in a couple of weeks. I'll be there. If you go, you'll see a kind of a similar talk to this, something much shorter. There's the ISTPNext workshop. Hopefully you've all seen that announced. We'll send out another announcement in the coming weeks once we get the website up. May 8th through 10th at APL. Things we're going to talk about are GDC and Dynamic as a great observatory and all the things that have to go in to that concept to make it happen. Solar and heliosphere and magnetosphere as great observatories. Again, what do we need to do to make that happen? The mesoscale heliosphere, what are the big science questions related to mesoscale dynamics? Tools and methods. There are a lot of tools out there. We're all transitioning apparently to Python. What's the roadmap for that? How do we get user input and things like that as a community? Numerical simulations across the heliosphere and the future science architectures. These are all things we're going to talk about at the ISTPNext workshop. So go back to your SPA newsletter if you missed it. If you want to be part of it, please email me or George Ho, or Luis Hara or Yuchifumi Saito, the 4 organizers. let us know you want to be a part of that or if you want to come. And then finally, Europe is organizing themselves, which is very nice to see. There will be a Heliophysics in Europe workshop, October 30th and November 3rd. ISTP has headquarters in the Netherlands. So again, about a year and a half ago, we established something called the COSPAR task group on establishing an international geospace systems program. Our motivation at the time was that we saw that magnetospheric physics in particular was lacking a cohesive scientific roadmap. It wasn't really clear where we're going as a community. I was pretty frustrated with the outlook, as others were as well. So we put together this group, and our goals then were to develop a roadmap and possible observation scenarios, engage in discussions with the communities and space agency representatives, and produce a COSPAR scientific roadmap for the publication in ASR. Well, in talking to the community last summer when I was giving the IGSP talks, and after Helio 2050 and before the white papers were due, we realized that we all faced the same issues, right? Magnetosphere, what we were facing was not special. In fact, what the magnetosphere is facing today is what the ITM community faced about a decade ago. And we're all converging on similar solutions. System-to-system, multi-point measurements, holistic observations of the system we're studying. So for the decadal, we did not put it in an IGSP white paper. I rewrote it a couple weeks ahead of the deadline and created an ISTPNext white paper. And that's the paper down here in the bottom right with all my co-authors that really helped put together a very nice white paper. We expanded membership in our COSPAR task group, including a lot of solar and solar wind people. And although we still have the same names, I didn't change the name, we are basically a task group on establishing ISTPNext. And we're still producing a COSPAR scientific roadmap. I'm hoping to get that draft out by the end of March. So what can you as a community do? Well, attend the workshops. Japan might be tough to go to in 4 weeks' time, but the APL meeting in May is, at least for me, right at the street. Please come to that. That is not an AGU-style science meeting. It's not even a GEM or SHINE type workshop meeting. It's a really nitty-gritty. How do we as a community organize? What are the obstacles to organization? What do we need to be doing to prepare for these great observatories that might be coming down the road? Think about how we can leverage GDC and Dynamic. Those are big missions. And how do we use them to jumpstart our vision? Now I'm part of GDC and Dynamic, GDC, so I'm using it to jumpstart the vision already. But how can we, a broader community, help establish a new method of collaboration? And then we also encourage you to advocate. It's a little difficult now with the decadal survey. They've closed their doors and shut their windows, but you still talk among community members. If you're not in the US, maybe in Europe, you can talk to your agency delegates, multiple ways to get your voice heard. Advocate not just for the vision of a integrated heliophysics community, but for the future health and vibrancy of our unified field. It's time to move, I would say, beyond the trance of scarcity, as we call it. It's important to speak with a common community voice. Use similar praise. System of systems is a word that we all use. I've heard headquarters use it now. Mesoscales is a tougher word to use because not everybody knows what mesoscales are. We often talk about mesoscale messengers, the dynamical change, connectors of systems. There's different words you can use, but again, mesoscales, messengers, connectors, system of systems, that's all, if you agree, start using the same words so that when we talk to different people, they know we come from the same community. And also speak in solidarity. Internecine warfare can have impacts beyond our community. You may not realize it, but people listen. People outside the US listen to what US scientists say, and that can actually cause some damage. So let's stop doing that. Let's be unified, because in the end, we're all on team science. And that was it. Thank you.
Right. Thank you, Larry, for a wonderful talk. This is a really great initiative to move forward with, especially as a younger scientist. It's nice to see some agree that it seemed bleak in the future, especially for the magnetosphere. It's nice to see stuff being put together to bring it back. So I have a quick question regarding the great observatories. Is this something you envision that would then be more less PI directed missions and more larger missions pulled from the decadal survey and then kind of put out very similar to what GDC was or what Van Allen probes was?
So it's hard to answer. For ITM, it's kind of easy because we have GDC and Dynamic, which are together. I don't want to say a number. It's going to be on the order of $1 billion, right? When you put all together, it's fairly substantial involvement, fairly substantial investment. And so we can use that as a strategic hub. Everybody knows about GDC, a big mission, can have a big footprint. And so it's easy to pull things in. Look at something like Themis, which we were a part of. That was a mid-X. It would be much harder for Themis to do this. Now, Themis did what it could do, had the ASI arrays, there was some radar coverage, some cluster conjunctions, but it couldn't really go big because it just simply didn't have the team, the resources. They're pretty, those competed missions are pretty slim in terms of people that are there. I think in order to make it happen, you either need a strategic hub, whether that's a NASA mission or a NISA mission or a JAXA mission. It needs to be a strategic science hub. So the international, with a long timeline, because our timelines are all messed up. GDC launches in 2029. That gives us enough time to pull things together. Or you need an ISTP type program. NASA or the agencies getting together and saying, we're going to make this work no matter what missions fly. We're going to make sure the architecture is there and in place for them to coordinate. Right now we have neither. For ITM we have GDC, a mission, but for Magnetosphere and Solar we don't have anything there. So at the ISTPNext workshop, this is exactly the topic we're going to talk about. So there are 3 sessions to start, one on ITM Go, one on Mag Go, and one on Solar and Heliospheric Go. And these discussions are what we're going to talk about. What's on the horizon? What's missing? How do we integrate all these things together? And if we need the agencies to do something different, we can ask the agencies to do something different. Now, they have no money. They might not do it. But at the end, if we're just off working our independent pieces already, and all we need is a little bit of coordination, we can make that happen.
Yep. So George has a comment. As an older scientist, he thought this was a great talk. And one of the things, I guess, as a pointer, is that we need to think about the political implications. The politicians will not necessarily understand the impact of what you're trying to do and what the community is trying to do.
Right. Yeah, so that's a good point, George. The politics take up half my time on trying to do this, particularly the politics in Europe. I do talk regularly to headquarters through GDC and through this vehicle. That's the headquarters, who've been giving me guidance on messaging, what words to use, what words not to use. So Nikki Fox told me once in a public forum, never use the word mesoscale because the policymakers don't know what mesoscale means. So that's why we came up with messengers and connectors and things like that. Europe in particular, we've been working really hard. And I want to say that European workshop that is happening at the end of October is the direct result of these conversations we've been having. That was a kind of a long way to get there. So yes, politics are really important. I'm not necessarily good at the politics. We have other people for that. But yeah, we're working on that messaging.
So Jerry's wondering if there's going to be a virtual option for the APL meeting.
There will almost certainly be. APL can certainly support that. Well, we want to have inclusion. Some of the stuff will be difficult to do virtually. Some of these discussions are really, you see it all the time. You can do some things virtually, but there's some things that just have to happen in person. So we'll have a virtual component, but I'm not quite sure at what level yet. We're meeting on Friday to kind of define what that might look like.
Okay. And so that announcement was made in the SPA newsletter a few weeks ago, if you want to follow up. Do we have any other questions? So we can open it to anyone else that might have any comments or suggestions. If not, I encourage everyone to get involved. I think this is going to be a really important thing in the future to help move the community forward and to keep the community cohesive, much in the way that it was during the Themis era, which I found particularly advantageous and great. It seems Themis was almost a much smaller scale of what you're suggesting. I think the ground-based array really showed that, in that how much additional science could be done with Themis with a small, rather small budget that still got some really nice science
Very
observations.
small budget, yeah, but just by integrating those 2 components, we got a lot of science out, right? Mm-hmm. So for the ITM, the GDC project, we're trying to even go bigger than that. There's a lot out there that you can get just by integrating things. It doesn't require huge investment.
Yeah, excellent. Well, thank you again, Larry, and hope to see everyone next week, where Tui Pulkkinen will be talking about the Solstice Drive Center. Hope everyone has a wonderful week. Bye.
Bye.